So this screencast is going to outline how to build the Arithmetic Logic Unit in Logisim. So this is a top level design. So you can see we've got an arithmetic unit, a logic unit, and then they're both connected to this multiplexer, which will decide which output to feed onto the ALU output. So we're going to use sub-circuits in Logisim to make it easy to build. We also need to note as well, so here A and B and Y are all 4-bit buses, because we're just going to build a 4-bit ALU, but it could be 8-bit, could be 16-bit, could be 32-bit, but these are buses, so we need to use multiple data bits. So I'll start off in Logisim. So this file main, I'm just going to rename this to bit ALU. So we know in the ALU we've got our 2 inputs on the wiring pin. So that's 3 data bits. I'll put that in, and that's A. We've got another one. So these are both inputs. B. Then we've got an output. Y. So start building it from the output. So we know we needed a multiplexer. So I can go under the plexers menu, select a multiplexer. So this again needs to be 4 bits. And because we're only picking between 2, so in here we've only got 2 options, we only need 1 select bit, because 2 to the power 1 just gives us 2 obviously. So I'll just leave the select bits as 1, and I'll drop that in. So I'll put another pin in. So this is just this select pin is just going to be a single bit. It's another input. So I'll just call that F for the time being. And I'm going to hook that up. Let's make it straight. Okay, I won't just leave it as it was. So now we need to build our arithmetic unit on our logic unit. So I'll create those as separate circuits. So add units, I'll call this AU for arithmetic unit. And I'll just create another one, LU for logic unit. So later I'll be able to just drag those in as sub-blocks once we've added the relevant input and output pins in. But we know for this ALU we need to be able to invert A and B, because we need to do the subtraction operation, so we need to be able to invert B and A to get the 2's complement, and then for some of the other functions we also need to be able to invert B. So this shows how we can invert the inputs, again using a multiplexer. So we've got our input coming in, we go through a 4-bit, again these are 4 bits, so this will be a 4-bit NOT gate into the multiplexer, and then F will select whether to invert or not invert A. So when F is 0, A will just go to Y, and then when F is 1, A will go through the NOT gate and then onto Y. So I can again easily build that in Logisim. Shift B down. So I'll just copy that, copy the multiplexer. It's got A going in. Select a NOT gate, make sure you select 4 data bits, YA is 4 bits. Put that in here. And I'll copy the pin. So that is F. I'll call it F0. And in fact, rather than drawing that again, I can just copy everything, drag it down, call that B, and then F1. So there. So with these 2 inputs, F0 and F1, we can choose whether to invert our inputs or not. So that's that part of the ALU done. So now we need to start implementing the arithmetic unit and logic unit. So the arithmetic unit, this is a simplified version. Because we can actually invert our inputs here, we don't need to invert the inputs inside the arithmetic unit. So essentially we can just use our ripple carry adder. So just to make it easier, I'll copy A and B, because again for a 4-bit ripple adder, we've got inputs A and B, and then we've got a 4-bit output. So again, I call this Y, A and B, and now we've got these pins defined in the sub-circuit. We can actually drag in the arithmetic unit. So I'll do a similar thing for the logic unit. So I've got A, B, and Y. So go back in the arithmetic logic unit, drag in the logic unit, and then we can build our top level ALU. So I'm just going to wire these up. So just connecting up the A and B inputs. So at that stage we've pretty much got our top level ALU done. Now I just need to implement the insides. So the arithmetic unit is just a ripple carry adder. So we change it into a subtractor by just changing the value what we put in the carry in. So the first carry in the chain when we're doing addition is 0. And then when you want to do subtraction, if you change it to a 1, that will essentially add 1 to your result. And then by inverting, so say we want to do A minus B, so we feed A into the arithmetic unit, we feed not B into there to give it the 1's complement, and then we can put a 1 into the carry in to make it not B plus 1, so we'll have A plus not B plus 1, which is the same as A minus B in 2's complement. So I was going to quickly build in the arithmetic unit, I was going to quickly build the ripple carry adder. So now each bit is just a single bit. So we need to use a splitter, so a 4x4 splitter. So the 4-bit bus goes in, and that then gives us access to each individual bit in the bus. So we'll do the same for B. Just quickly build this. So they 4 full adders, each one's a single bit, and I'll hook it up quickly. So that's A0. So it's very important when you look on the splitter, you can see the least significant bit 0 is labelled. So that's A1, A2, A3, and then do the same for B. B0, B1. It's not very neat wiring, but I don't really care. B3, and all the carries just end up rippling the chain. And then we need to use a splitter again to recombine them. So splitter is not really probably the best name for this component, because we can actually use a splitter to kind of recombine. So that's that's bit 0 the output. So then all the outputs are connected together. You just need to be able to handle this carry in and that carry out. So we just need single pin. So that's so let's call that C in for carry in, and then the output is a carry out. Let's call that C8. So that's a 4-bit ripple adder. Oh, could I change the inside? Because the C in and C8's appeared, it's messed up the previous wiring, so I just have to redo that. And so Y. It's got A. And B. So now this carrying determines whether, essentially is this F. So when the carrying is 0, we'll do addition. When it's 1, we'll do subtraction. So I'll put another input pin in. So we've got F0, F1, so I'll call this one F2. So this pin will determine whether we're doing addition or subtraction. And then we've got the carry out, so we need to have a an output for that, so make it an output. Oops. So I know that from the test vector, I've called that, I often use uppercase C for the carry flag. So that's our C flag here. So we kind of got this bit of the ALU done now. So we've got F2 going in, selecting between addition, subtraction, and the carry out coming. Now the logic units. So I'm just going to disconnect these because I'm going to modify what goes in. So we can from these logic operations, we never need to have not A. We're always using just A. So we don't need to, before it's connected up to this part. We can actually just connect it to A itself. So I've got A going into the logic unit, and then either B or not B depending on the value of this. So logic unit, again we've got a multiplexer, but now it's 2 select bits because we're selecting between 4 different operations. So we'll put that in. So we're going to have a 2x2 splitter because this select is a 2-bit bus. So I'll use a splitter. Now we've got 2. So I'll put that pin in, so that's a input pin. So we've got F0. And then F2. So the values of these will select which logical operation to do. So we'll start putting our logic gates in. So these are all have to be 4 data bits because again A and B are 4-bit buses. So we've got AND or exclusive or. connect those up. And the last one, it's just B or not B. It's pipe direct to the output for the move operations. Put that, so connect all, put the ones to B. And that looks like it for the logic unit. So go back to the ALU. So now we've got these two. We've got F2, so that needs to be connected up to here, and F0 needs to be connected up to here, and then arena has to be F3. So that's the ALU essentially done. Now we need to put the flags in. So we've already got the carry flag in and the overflow flag. So I need to, for the overflow flag, back in the arithmetic unit. So this is a XOR gate. It's only a single bit now because we're just looking at the carry in and the carry out of the most significant bit. So essentially when the sign bits are different, that's when you know overflows occurred. So I'll add an output pin for that. That's overflow. Let's go back to the. Just need to be careful with these flags, not move that in. Again, for the test script, the overflow flag is called V. Okay, that's what's happened here. Okay, that seems fine. And then we need to do the zero flag. So the zero flag's pretty simple. So we need to split off the output bus. So 4x4. So we need to get access to all these bits. And we can stick them into 4 input NOR gates. So when all the inputs are 0, we'll get a 1 on the output. So change the number of inputs to 4. Zero, 1. So that's a 0 flag, so that's called Z. And the final flag is just the negative flag. So that's essentially the sign bit. So when the sign bit is a 1, we know the number's negative. So that's N. I'll just connect that up to bit 3. So the opcode itself is actually a 4-bit value, so we need to be able to handle that. So I'm going to add in another 4-bit input. Opcode. And then we'll use a splitter to get those. So I'm actually going to delete these pins. So that's F0. That's F1. F3, just delete that. And F2. So rather than using individual inputs, we'll actually just use a 4-bit input. So we should be able to test it now. So look at the test vector. I'll just rename those because they're lowercase. So A, so it matches what's in the test vector. A and Y. So that's all passed. So that's a fully functioning arithmetic logic unit.